Okay, any new ideas to how to prove that the Earth isn't flat? So maybe this one. So I was surprised nobody mentioned that the old way to prove it and to measure the curvature is the measuring shadows of sticks in different locations. So if the Earth is indeed curved, and then you put a stick here, the exactly same height. Okay, so the sun is here somewhere. Okay, so then the shadows will be, so let's see, the shadow will be shorter than the other one. Okay, like this. Right. Okay, so that was done 2,000 years ago or so by ancient Greeks. And they measured the Earth, the circumference of the Earth and the diameter of the Earth, and pretty well actually. And the Columbus should have known better. That was known to be way 1,500 years before that, and he was like wrong by. They were wrong maybe by like 5% or less, and he was wrong by what, 50% or I don't know, something along those numbers. So he could have done this himself and figure it out. So the problem actually came up. The advantage of this over the other two that was suggested. One is take a taller building, look at a taller building, walk a taller building, and then maybe halfway you're going to see this much of the surrounding area. And if you go up, you'll see more. Okay, so that is the difference. Indicates the curvature of the Earth. And the other one was as you're moving away from a tall building, then at some point it will disappear if you're far enough. Okay, so all of the good these are two good methods, except you got to live in a desert or prairie or near the ocean to test these. You got to have a flat. Just look outside. There's no way you can apply either one of these two methods, right? So this one a little bit better, but also has a problem. It actually came up in the other class, and the student said his grandmother does not believe that the Earth is round. So, and he tried to prove it. And well, the idea that I suggested would just try to use like a smartphone. And then you can, if you are here in Huntington and you live somewhere else, you can at the same exact time together measure the length of the same stick and see that it is different, and then maybe it will be convincing. Yeah, you got to have like a perfectly vertical on a probably like a level thing. Okay, so that it would be vertical, and then you need the ground also vertical, so you need a level. Okay, so it takes some work. And then there is actually a flaw in this argument. They're supposed to prove that the Earth is round, and there's a flaw there.
Yeah, if you're on like antipodal points of the Earth, it'll have the same. Or no, that's not true. Of course, that's not true.
No. The flaw is kind of I don't want to tell you about it. It is if well think about it. I think that if somebody in a so put yourself in the mind of a person who does not believe that the Earth is round and find the flaw in this argument.
If the sun is closer to Earth, then it would make the shadows longer.
Yeah, you kind of you're on the right track. Yeah, closer. No, actually, closer it wouldn't help. I don't think it makes a difference. The point is okay, I'll tell you. If person believes in flat Earth, at least some of them believe that the sun is actually. Well, let me show you. How large the sun you think that it is? Okay, two sticks, same height. The sun is like a street light. Okay, like this. And then it throws light like that in the radial directions, and that will produce different lengths of shadows, even though the Earth is flat. Okay, so you can see, right? So it's different length on a flat Earth. Okay, so, well, so the argument fails. I mean, that's no joke. You cannot prove it this way. Okay, so if remember the round disc with a kind of a hemisphere, a glass hemisphere crystal with the stars and suns on top of it, some of them moving. Okay, so they might be small, and like I said, they like a street light produce a different lengths of shadows. Okay, so well that's it's so far as we know, it still might be a flat. Okay, so we did the plane. Okay, so this is where we have discovered that the best way to represent the plane is through the dot product, and this is really pays off. That you see the investment into new concepts that might seem complicated early on. It pays off when it covers so many things, and then you just discover the connections on again and again as you progress solving different kinds of problems. So we were trying to find a formula for general formula for a plane, and then we discovered that the right hand side of that plane is in fact a dot product. And then we took it further, and we actually discovered that the next one that it also can be done in any dimension, and you don't even need to extract z here as I did. So that part is really only necessary because our actual interest is functions of two variables, and then that z is the third variable. It is separate in the left hand side. Okay, but in general, suppose you're not doing any calculus of functions, all you want is just a plane, and then this is the equation of the plane. Any plane, including in 3D, it would include also all vertical planes. Okay, so to make that, so the construction is right here. So you start with nothing but a point and a vector sticking out of it, as long as it's not 0. Okay, then you discover all the possible vectors perpendicular to the vector m, and together, including all different magnitudes. Magnitude doesn't matter; it's only the angle that matters. Okay, so and then they will form a plane. So you could take it as the definition. I don't think I put it this way, so let me state that. So given a plane. Given a point in R3 and a non-zero vector m. Okay, then all points in R3 that satisfy and dot, say OP. Hold on, where's the point? P naught over here. Or it could be O. Say how about OP, like this. Is equal to 0, or which is the same thing, and perpendicular to OP, form a plane. So that's the definition of a plane. You can say, because otherwise we haven't defined what a plane is to begin with. But if we just speak of in terms of analytic geometry, the equations that we have, we could simply define anything we want in terms of relations between points. And once again, for two given things, a point O, which may or may not be the center of the coordinate system, and then all we need is what's left is the dot product. Okay, so the dot product gives you 0 or perpendicular. The second version is slightly not quite perfect because the dot product of 0 is not equivalent to two vectors being perpendicular, because it excludes, the latter exclude the point O itself. So plus O. Okay, so on the left, if P is equal to O, then you still have 0, but you cannot say that vector OO perpendicular to n, because there is no such thing. Okay, so they form a plane. We certainly it's worthwhile asking ourselves what happens in high dimensions. So what about Rn? The equation can be written in the exact same way. Once again, a vector in Rn, a point in Rn, and then you still have an equation, n dot OP is equal to 0, and the second interpretation still works as well. Remember, we define angles in the n-dimensional spaces. Okay, so that still holds in perpendicular OP. So then, what is what is that we end up with in a high dimension, say dimension 4? And the answer is well, the answer is actually, you can guess if you go back rather than forward, go down in dimensions. So start with R2. So once again, you have n dot OP is equal to 0, or n is perpendicular to OP. What is it? All vectors perpendicular to on the plane. So we have a vector, we have a point P, and then we a point O, and then we have a vector n, and then what is it? All vectors perpendicular to n through that starts at O. What do we get?
Just a line?
It is indeed a line. So there's not a lot of variability, because it is just a two-dimensional space. So in other words, the answer is to this question is it is a kind of a plane. Okay, so line in R2. Then we know that it's a plane in R3. And then what is that in R4? And the answer is, you can guess, what is it?
It's like a part of R4 that's as big as R3?
Yeah, that's right. So our line is R, plane is R2, so this will be R3. Sometimes it's called a hyperplane, and all of them are hyperplanes in the sense that hyperplane meaning that it's dimension 1 lower than the ambient space. So in R4, one dimension down, you have R3, which is our three-dimensional space. Okay, and it fits in this four-dimensional space, and in fact, it is very thin. So just like that line, this is on the plane, right? This is on the plane, and that line is actually very thin, even though it has dimension 1. And then you go higher, it is a plane in space. It's still very thin, okay, in comparison to where with the space contained. So this is, once again, we say R3 is very thin in comparison to R4. So it's like a what is it? So imagine that our space looks like this. To a four-dimensional person, it looks like this. Okay, and he can do this. He can do this to our space like that. He won't even notice because it's so thin. Okay, so we're not going to go there, even though it's technically every time you go on with dimensions, with rather the number of variables, from functions to two variables. Right here, okay, now we go to functions of three variables. That's where we are. So a linear functions of three variables will be this, okay, and so on and on and on. So it is all fits into our plan of studying functions with several variables. But we put it off for a while, and we go back to functions, but of just two variables. So functions of two variables. And once again, let me write that equation that we already had. So it's the same equation. Well, let me do it this way. So the equation is n dot OP is equal to 0. Okay. So now, since we decide to look at functions of two variables, so the vertical planes are up. They cannot be graphs of functions of two variables. Okay. So they are out. So like this is not it. But what about the normal, remember the term normal vector of that plane? It will be horizontal. And, okay, so if I'm trying to throw these planes out and then see what it does to our formula. And it does something that is just, we will take us back where we started. So if n is horizontal, then well, and now we say we don't want those, which means that then n has a non-zero vertical component. So it has two horizontal action y, and the z is the vertical component. It is non-zero. That's what distinguishes this situation from this narrow situation that we're looking at, functions of two variables. Okay, so those that satisfy the vertical line test. So it has a non-zero vertical component, firstly, and secondly, we could say that lengths don't matter. Why they don't matter? Because we only talk about angles. So n could be longer, OP could be longer. So that no concern to ours. So of ours. So then what it means is that let that component be 1. So in other words, if we make it longer or shorter than vector n, it does not change our plane. So then n will be indeed 1 m n. Okay. And then what happens to our equation? It is so n dot op is equal to 0 becomes 1 m n dot times what is it? OP will be xyz minus abc equal to 0. Okay, so this is our point. This is our point, which is the variable point p, the fixed point O, and the vector n is the vector of as we described it, as a vector of slopes. Except it will be a vector of slopes, but it is still better to think of it as a vector normal to the plane. It is when we're going back to functions, we realize that these are two slopes. Remember that exactly what we did last time. These are actually two slopes of the plane in the x direction and in the y direction. But if we now multiply this out, what we're going to have is n is the last 1 is the last component of the first component. Sorry about that. So it's mn1. mn1. The z component is 0. mn1. So if we multiply, then we're going to have the equation that, let me just multiply it. So have mx minus a plus n y minus b plus 1 z minus c equals to 0. And then I could write it in the standard form for functions. I solve for z. And it will be equal to c plus mx minus a and y minus b. So it's the same plane, it just happens to be non-vertical, and then the rest is the same. The rest is the same. So the point is that it's still passing through. So it's plane first of all. Why? Because it's a linear function. Okay. Secondly, it is passes through point ABC. And it has slopes m n in the x and y directions. That's what we talked about just like last time. So looking roughly like this, I probably should put it in the right place. So if this is x and y and z, then we are, these are the two slopes, one, and this is the other. Okay, in the x direction is, say, this, and in the y direction is that. Okay, so so that is the formula that is really useful for the time being. The previous formula is more general, and it is useful for whenever we get to study parametric surfaces. So not functions with parametric surfaces, just as we moved from functions, numerical functions to parametric curves. Here we're going to move eventually from functions of several variables to parametric surface. Functions of two variables, which does produce a surface, but it's a special kind, to parametric surfaces, and then they will have tangent planes, also parametric, and that's where that formula is going to help us. Okay, so let's see. So that is going to be used a lot for actual when we get to do differentiation in calculus in dimension 3 of functions of two variables. Okay, so that is going to be the linear approximation of a function of two variables through that point. And so you will, m and n will be those two partial derivatives of the function. But at this time, let's just put derivatives aside for a while and just look at functions, just functions of two variables. A few examples as quickly as possible, but they just we just have to do it just to get some more practice with dealing with functions of two variables without using derivatives just yet. So this is a linear function. This one is given in this particular point slope form, yes, but the another one is just z is equal to f of xy is simply equal to a plus bx plus cy. Okay, so that would be a linear function of two variables. Okay, and so I certainly can plot it, and I have here. So that's a curve. This is a plane. Okay. I do what I just mentioned. This is what's going to happen eventually. A plane and a tangent plane. Okay, so that corner over here, we're going to plot a tangent plane. Right now, we're just looking at functions, examples of functions. So one is if this is a linear function, what makes it linear? So it is a linear function. What makes it linear?
All of its dependent variables, they have exponent 1, like there's no square root or sine or anything like that?
Yeah, so x and y appear with first powers, but let's not, that's sometimes easy to overlook. Is this a linear function? No, because
it involves the product of the two different variables.
And so when you multiply, you have powers. Okay, so technically it's x1 times y1, so power is 2. So that's why this is not a linear function. And in fact, you can discover that it is possible you have two variables and they're independent. Okay, so even though they're independent, but it's also up to you to make them dependent if you want to. And what I mean is just set x equal y, and then your function f of xx is equal to x squared. Okay, so what did I do here, geometrically speaking, when I set x equal y?
Did you restrict the graphs so that?
Yes, yeah, I did restrict the graph. Yes. So that's how we study functions of two variables, and you restrict the graph so that a function of two variables, so that what's left is a function of one variable. We already did that. The simplest one is you set, say, so let's take the same function. So f of xy is equal to xy. What I could do is set y is equal to 0. Then what do I have? My function f of xy becomes 0. It is in fact does not depend on anything. Okay, so but the point is that this is the restriction part is right here. I am setting y equal to 0 while x is still a variable. The fact that it does not appear at the end, it doesn't matter. We are restricting our inputs. This is what we do. The restricting the graph is really not as much as restrict the domain, maybe a better way to put it. We restrict the domain so that what's left will be a function of one variable, and it is fairly easy if you just pretty much any straight line through the xy plane will give you that effect. So what I just did, I picked this one, this one. This line, the x-axis is y equals 0. Okay, on the xy plane, and then suppose let's not try to plot the graph of the function, but rather just examine it, what we would do if we want to figure out what the graph looks like without actually plotting it. And that's what we do. We restrict the domain by probably a straight line, and so then the function becomes a function of one variable, because this is a function of variable x only. If you can confirm that if you put y equal 1, then f of xy is equal to x. Okay, so this fact that I already drew, f of x equal to 0 means that the elevation is 0. So then the part of the graph that comes from here is this. So the graph of this function, actually this function has straight line. This is a straight line. It has another straight line which is over there, right? So I fix y equals 0. This is y. So this line is y equal 1. Okay, and then it produced the elevation. So you are imagining what the part of the graph looks like?
It seems like the graph is, it's like a three-dimensional version of the absolute value, kind of like it has.
No, it will be a straight line. There won't be any break. It is purely x. It just will go like this. You see what I'm showing? So when this is what you see when you put your if you stand your cell, you stand here. So that is your eye. You are looking. You let the y-axis go right into your eye, and then what do you see? You see this y equal x. The graph looks like a straight line from x to y. So it will be going like this, a straight line. So this line is horizontal, the previous line, and then it becomes this one has a slope. Okay, and then on and on. If I say y equal to f of xy is equal to well, this is the way it is actually done. You just replace y with that number so that we would have we would emphasize the point that it's a function of one variable. So this will be 2x. So what happens is the slope increases. So I don't think I actually plugged it the right way. So this one looks like this, and going down there, and the next one along y equal 2, it will have a higher slope. Okay, I'm just trying to demonstrate. Maybe like this. Far from perfect, but it gives you ideas, and then you sort of, if you collect enough information, you can figure out what it is. It is interesting that so far the whole surface is made of straight lines. Okay, we have in fact more horizontal lines, if you like. Now if I put x equals 0, then f of 0y is 0. So what did I just discover? There's another straight line in this. Where is it?
Along the y-axis?
That's right. That's the y-axis. What I just found is the y-axis, this one. So this part, this blue line, is in fact also lies on the graph, on our surface. And then if I keep going, then x equal to 1, then I have f of 1y is equal to y. So it is here. It is starting over here, and then it goes up. Okay. And then I go with x equal 2, and once again I have 2y here, and the slope increases over here. Okay, so straight line, straight line, straight line, and now back to what was done just we started with, x equal y. It means that we restrict our domain to the diagonal, and the diagonal, by the diagonal I mean this. So about that diagonal, okay, now what lies above this diagonal?
parabola?
A parabola, right. So parabola here. So it turns out that it's not all straight lines. It's certainly not a linear function. It actually has a parabola above this. So it is actually harder to imagine making these steps than to actually plot it. So let me plot it. xy is a simple function as that. In fact, this is function sine xy, which is almost as a function very similar. Not similar, but more complicated. But let me start from scratch. So this is simply xy, what I'm plotting. Okay, so I'll just remove sine here. That's all. So as you can see, x above x, y. You can see I'm making y horizontal and x vertical because as you can see on all these pictures, y axis. This is the y. The x axis is facing me, and the y axis is pointing to the right. Okay, so that's why it's on the screen. This is going down, but on my tablet, this is pointing at me, and y-axis to the right, but the x-axis pointing at me, just like on that picture. Okay, so that's the thing. Okay, now let's remove sine and keep everything else. Okay, and okay, so let me change the data. Okay, right and down. Okay, okay, so that's in the center. How about I put -1 here and here too? Okay, do you see what this is? Let me make this slightly larger. Do you see? Okay, let me rotate it for you. Design. Okay, there's this 3D rotation. 3D rotation. Okay, so I can rotate this. Rotate. Wait. No. Okay. It looks kind of flat. Let me shrink it. It's more pronounced. Okay, you see what it looks like now?
It's like a saddle?
Yes, it is a saddle. There is a very nice name for it. The hyperbolic paraboloid. Hyperbolic paraboloid, and in a minute. Well, you see any hyperbolas? We already saw parabola. Remember that we started with it is a parabola. Y is equal to x squared or y squared. You see any hyperbolas? It's right there.
The cross sections of the z-axis.
That's right. This is a hyperbola, and that's also a hyperbola. So a bunch of hyperbolas, and that's the next issue: is how we restrict the graph rather than restricting the domain. We have been cutting it. We have been cutting it with vertical planes, as we have many times. But there is sometimes a better option to cut it with horizontal planes. Okay, and in that case, let me show you. So the same equation. So cut with a horizontal plane. And they all have the same equation, z equals something. So how about z equal to 1? Then what I have here is xy is equal to 1. So our formula is z equal xy, so I fix z equal to 1. Then the equation I end up with is x equal 1, and in other words, if you insist, it will be y equal 1 over x, and you have your hyperbola. Okay, and then certainly you can see how what's gonna change if I change z. If I change z, nothing much gonna change. Still that number will be decreasing, and then all of these will be hyperbolas. So the vertical cuts are either straight lines. We have a bunch of them with different slopes. Then unless you cut, if these planes are parallel to the axis, to the axis, yes, vertical planes parallel to the axis, then it gives us straight lines. If we cut diagonally, we have a parabola. If we go diagonally this way, one parabola, that's another parabola, and if we cut it horizontally, we get a bunch of parabolas. Okay, with one exception. If z is equal to 0, what do I get? Just solve the equation. So in other words, find all xy such that xy is equal to 0. Can you find these? Two numbers multiplied equal to 0. What can you say about them?
One of the two is equal to 0.
At least one, yes. Either x or y is 0. So what was it geometrical? When x is equal to 0, what is it? On the xy plane? X equals 0. X equals 0 on the xy plane.
Y-intercept.
Or if you mean y-axis, then yes. It is the y-axis. So, this one. Right? X equals 0, x equals 1, x equals 2, x equals -1. And similarly, y equals 0 is the x-axis. So, then the answer is this. The answer, the solution to this equation is two x's. This is the answer. On the xy plane, the result is two straight lines, and they are visible almost. They're almost visible here, right? One line and the other line. So two horizontal lines, which is certainly also an indicator of the limitations of our partial derivatives, because there is no, if you're standing in the middle, okay, and if you try to go either along the x-axis or along the y-axis, there won't be any change. Okay, so it looks entirely flat. And that is the only, if you stick to slopes with those two directions only, then it won't tell you the story, because it looks like nothing is happening. It looks like it is flat. Even though, as you can see, we have a drop here, we have rise there. These are two parabolas. So two parabolas attached to each other like this create a central point. Another thing that is hard to recognize here, but it is Pringles. Pringle, chips. They are well known to have the shape of the hyperbolic paraboloid, which is crucial because so it's made of straight lines. Apparently, there's some advantage to that. It's easy to stack. At least that's the version that I've heard, but there is some kind of difference. So first of all, flat is of course easy. You just stack them easily. What other shape would stack as well? If you look at, for example, hemispheres. So I'm not sure why this has advantage over stacking hemispheres. So just stack them. I think the difference might be the the horizontal distances versus vertical distances. So you stack one hemisphere on top of the other, and the distance is vertical is the same, but horizontally you might have it gets thinner and thinner. That's what I mean. And if you just lift it, something like this. So it kind of rests on the edge rests on the surface. And the advantage of a Pringle, I suppose, that no matter from what direction you see, it actually looks like a straight line. And so he stacks straight lines in the same exact manner. Not only the vertical directions are the same, distances are the same, but also horizontal and any other direction they are stacked. So in particular, that this one is as good as if you put your can on side, it will still be a stacked well. This one will not, because the gravity will be pushing in a different direction. So, well, that's the best I can tell right now why it's supposed to be advantageous. But it's kind of fun. The shape is nice. It's easy to make any other shape, by the way. It looks roughly the same, but does not satisfy this nice property of something made of nothing but straight lines. So literally, you can have a bunch of straight lines and build a. There might be a picture, not a picture, but rather like a prop on this floor somewhere, which is to illustrate hyperbolic paraboloid. You make it of ropes. So just string like a frame, and then you just have a bunch of ropes, tight, and then you see that if you just step back, they kind of form a surface, and you can see that they're definitely made of straight lines. Okay, so what else? What other surfaces that we might be interested in? Let me quickly see if I have anything. This one, let me remind you of this one. Some time ago, when we talked about the gravity force, as it is inversely proportional to the square of the distance, so that is a function like that. You can also see the problem that we have to face, just as always with functions, and it is the domain. So in this particular case, the function simply being 1 over square, simply x squared plus y squared. That is our function. 1 over x squared plus y squared. It is so. This is this. Remember that the distance is distance between point x and 0. I'm sorry, point xy and 0. Xy and 0 is x squared plus y squared square root. If you square it, so that's what gravity will give you with some coefficient. And then the question that always is asked inevitably about what is the domain. And the domain, once again, you have to make sure that the formula that you've written makes sense, and you find out for what values of x, y it does not make sense. All the way the functions we have seen so far make sense for all x, y, not this one, because there's a chance of division by 0. And then so you have to, just like in calculus or pre-calculus, you just take x squared plus y squared, set it equal to 0, and solve. Except, you see the challenge now, you have two variables. Just that problem we just had, xy equals 0, is exactly the same problem we have now. You have to find the answer is not a number, not even the two numbers, or interval sometimes is not, it was a possibility. Now it is a solve means find the subset of the plane. So xy, that satisfies this equation. Or inequality. Okay, so x squared plus y squared is equal to 0. How do we solve it? One number is positive, non-negative. The other one is non-negative. So what is the point? When you have to go into this is kind of extra. We really know what we're talking about anyway. Define all the points, the distance of which to 0 is 0. Well, there's only one point like this, right? So the answer is 0, 0. There's only one point, zero distance from zero, it's the point itself. Okay, so then if you want to plot it, you do it like this, plot it just like in pre-calculus, and you draw a hole, and then, so this is the domain. Okay, so you can certainly think of other examples, maybe 1 over xy, we just discussed this, right? So what's the domain? Set xy not equal to 0 solve, and then exclude it from the plane, since the solution to this equation is the x's, then you're left with, on the xy plane, you exclude or cut out everything but, well, you keep everything but the x's, and that is your domain. And so on. Okay, so that's how the domain issue is addressed, and then you can have square root, and once again, then you end up with an inequality. Say if you have 1 over x plus y, square root, is that's your function, then you have to find the domain. Once again, you have to take your xy, x plus y, and solve for what values it is negative less than 0 to exclude it, and sometimes, just as in one variable case, you frequently replace an equality with an equation. X plus y is equal to 0, and y is equal to negative x. So what we're looking at is a straight line, and then that equation gives me the edge of my domain. So what is my domain then?
It's all the plane minus that line.
No, we only one of them, right? So, for example, if both x and y are negative, that's not going to work. So this gives you the edge. It's not what we're cutting out. It's what it is the edge of the domain. So this is the edge of the domain. So you're left with this. The line itself is included this time. Okay. All right. So we'll just resume tomorrow.